Hello, everyone. Welcome to the part two of the lecture. Uh, as I mentioned at the end of the part one, we will start with a new example here, and then we will go into the random variable version of Bayes' theorem. And then after that, we will look at some other topics. The example was taken from the Mood, Graybill, and Bose book titled The Introduction to Theory of Statistics. Let a random variable y represent the diameter of a shaft, and let a random variable x represent the inside diameter of the housing intended to support the shaft. By design, the shaft is to have diameter 99.5 units and housing inside diameter 100 units. Suppose that the manufacturing process for each item is imperfect, so that y is uniformly distributed over the interval 98.5 to 100.5, and x is uniformly distributed over 99 to 101 interval. What is the probability that a particular shaft can be successfully paired with a particular housing when successfully paired is taken to mean that capital Y is less than capital X and greater than capital X minus H for some small positive quantity H? Assume that X and Y are independent. So this problem can be shown using a diagram like this. We have a housing in which the shaft is going to be put inside. So the housing, the inside diameter of housing is a random variable uniformly distributed in the interval 98.5 to 100.5. Sorry, X is distributed as 99 to 101. Y is the diameter of the shaft. It is also uniformly distributed in the interval 98.5 to 100.5. So we say that the shaft can be paired with the randomly selected housing successfully if this Y, that is the shaft diameter, is between X minus H and X, where X is the diameter of the housing, X minus H will be a smaller value like that. So that means if we can put the shaft like this with a small clearance, then that we say that they are successfully paired. So we are interested in finding out what is the probability of happening this kind of situation. Now, we don't want H to be quite large. In that case, this will be too uh, loose. So therefore, we would like H to be a small value. But in this example, I'm going to take H as 1 for simplicity. But you can replace that one by some other value when you're doing the calculations if necessary. So X is uniformly distributed in the interval 99 to 101. Y is uniformly distributed in the interval 98.5 to 100.5. And suppose H is equal to 1. So we are interested in this probability. Probability Y is between X and X minus 1. Now H is equal to 1. Right. So how do we find out this probability? We have to integrate the joint density function of X and Y on the set representing this event, right? So event will be, in this case, set in the two-dimensional plane. It will be a subset of the support of the joint density function. Right. So this is what we want to do. We want to integrate the joint density inside on some set A, where I have shown this set A in this picture. I will explain in a minute. Right. So what is the joint density in this case? Joint density function is going to be the product of individual densities, marginals, because x and y are independent. So what is the marginal density of x? X is uniformly distributed in this interval. The length of this interval is 2. So therefore, the density function will be equal to 1 over 2 in this interval when x is in this interval. Y is uniformly distributed in this interval. The length of this interval is also 2. So therefore, the marginal density function of y will also be 1 over 2. So therefore, the joint density function will be 1 over 2 times 1 over 2, that is 1 over 4, when x is in this interval and y is in this particular interval. In this case, we don't have any other restriction combining x and y. So the support of the joint density function will be this rectangle in this here in this picture. X is between 99 to 101, y is between 98.5 to 105. So xy, when xy is in any point on this in this rectangle, blue rectangle, the joint density will be a constant 1 over 4. Right. But what is this set A now? Set A has to satisfy this condition here. So that means y less than x and, y greater than x minus 1. So in order to find out that sub-region, we will look at y equal to x line and y equal to x minus 1 line. So this in this picture, I have drawn y equal to x line is this blue line, blue dotted line. Y equal to x minus 1 is this orange dotted line. So therefore, this A here, the area on which we want to integrate the joint density will be given by this sub-region here indicated with the angled line in orange color here. So what we want is actually the integration of this constant 1 over 4 over this particular region A, right? We can do that very easily using integration, doing integration in 3 parts. First of all, integrating over this area, plus integrating over this area, plus integrating over this area. That is one way to do it. But I think it is even easier if you calculate this probability by taking 1 minus the probability over this area and this area, blue area, this triangle and this triangle. And this triangle is area of this triangle is the same as the area of this triangle. So therefore, it is enough to integrate the joint density over this triangle and then take 1 minus twice the area of the triangle times the height of the joint density. So therefore, that is the method that I have used here. So the probability that y is between x and x minus 1, where this x is also a random variable, notice that, is equal to 1 minus twice the height of the joint density times the area of a single triangle here. So area of the triangle is equal to the length, this length times this length divided by 2. So the length here is equal to 1.5. This side is also 1.5 units. So therefore, the area of the triangle is equal to, excuse me, 1.5 times 1.5 times 2. So when you simplify this, you get the answer 0.4375. So therefore, that is the probability that if you randomly select housing and if you randomly select a shaft, the probability that the pair will be successfully meshed or paired is only 0.43. So it's you can see that when you consider this uh, the intervals in which x and y are distributed, there is only a small certain amount of overlap, right? So if xy point is outside that overlap, then it will not be able to uh, successfully connect them, right? Put one inside the other, right? So you can see that the probability that randomly selected housing and randomly selected uh, shaft will be meshed is actually even less than zero point 0.5 here, right? Okay, so anyway, that's how you answer that kind of question. That's a kind of an interesting question to me, actually. It's a practical question, right? Now we go to the next item, that is uh, the Bayes formula for random variables. Here I'm considering again the continuous case only. You can find out the formula for the discrete case very easily, analogous one, right? So here we are looking at, suppose we know the conditional distribution of y given x, and also we know the marginal density of x. Then using that knowledge, here we try to find out the conditional distribution of x given y, right? So we know the conditional density function of y given x, and we also know the marginal density of x. And using those two, we are going to find out the conditional distribution of x given y, right? So this is very similar to what we know about the probability of events, right? When you talk about the basic Bayes theorem, right? If you remember, let me write it down for you to recall. Let's recall it. So we know that for events, we say probability A given B, we can write down as probability. First of all, if you discuss completely this one, that is by definition, this is the probability A intersection B divided by probability of B, given that if probability of B not equal to 0. So now this part I can write down as probability of B given A times probability of A, and then divided by probability of B, right? And this one we can usually write down using if there are several events, right? So in order to discuss Bayes theorem and also total probability law, usually we have to have a situation like this. Suppose you have several events A1, A2, A3, A4, A5, and so on, which are mutually exclusive and exhaustive. And suppose you have another event B, right? So then probability of B we can write down as probability of B given A1 times probability of A1, and so on, up to probability of, say, B given, say, AK times probability of AK, right? If there are K number of mutually exclusive and exhaustive events, right? And similar to that, so we can replace this thing by this expression. So you can see that this expression is very similar to this one. What you have instead of the probability, now you have the what you are looking at here is this is like A in this situation, but it's not a random. This is an event. This is a random variable. This is an equivalent term here is B here, right? So what you are looking at here is density of B given A, right? Remember again, this is not that. B is an event, Y is a random variable, so you cannot say they are equal or something, but something similar, right? So probability, the density function of Y given X, evaluated at Y times, so like probability of A, here we have fx, x, the density function of x. So here, this one is actually a summation of probability B given AI times probability of AI. So similar to here, we have integration of the density of Y given X times the density of X. So you can see that it's completely similar, but of course they are talking about two different things. This is the density function. These all are here. We have density functions. In the previous one, we talked about events. Right. So that is the Bayes formula. If you want to get the conditional distribution of one variable, say x given y, you can get that one using the conditional density function of y given x and the marginal density of x. Right. So let us look at an example. Uh, Suppose you know that the conditional distribution of y given x is normal, which mean this given x and say standard deviation and variance 1, for example. Right. So the conditional distribution of y given that x is equal to simple x is normally distributed. So for example, if x is equal to 1, then y will have a normal distribution with, if x is equal to 1, then y will have a normal distribution with 1, 1. If x is equal to 2, y will have a normal distribution with 2, 1, like that. Right? The mean is equal to the given x. And the marginal distribution of x is normal 0, 1. Suppose the marginal distribution is equal to is standard normal. Find the conditional density of x given y equal to y using the Bayes formula. Right? So we have to directly apply, but in the it's very straightforward. Only thing is difficult thing here is we have to do this integration. When you are doing the integration, we have to be a little bit, we have to do a little bit of mathematics. Otherwise, it's just direct application, direct application of the formula. So the first term here in the numerator, what you need is the joint density function, sorry, the conditional density function of y given x is equal to x times the marginal density function of x. Right. So both are given to us. The conditional distribution of y given x is normal with mean x and standard deviation 1. So that is this part here. Right. So this is the normal density function with normal distribution. Density function with mean x. The density function is evaluated at y. Standard deviation is 1 and the variance is therefore 1. And this is the marginal density function, which is the standard normal, is a function of x. That is the marginal density function of x. So when you simplify, you get this expression here. Now, to get the denominator, we'll have to integrate this with respect to x, right? From minus infinity to plus infinity, because x is standard normal, x varies from minus infinity to plus infinity. So we need to find out this expression, right? So that is the difficult part, if there's any difficult part. So, but we can do it using a little bit of mathematics. Okay, let me remove this first. So we can write down this expression here. This part here, like this. Y minus x square plus x square is equal to the square like this, and then plus y square over 2, right? So therefore, the integration will be given by this expression here, right? And you can substitute this expression here and then do a little bit of mathematics like this. And then you will be able to get this expression as, remember we are integrating with respect to x here. So all the terms with only y, you can take it out. So then you can see that you can write down the remaining part with the integration as the integration of some normal density function. Actually, you can show that this is this part that you get after simplifying this. is actually a, density function of a normal distribution uh, with some x minus mu over some sigma square. Remember, the normal distribution uh, uh, function has 1 over root 2 pi sigma divided by sigma, and then e to the power minus x minus something divided by sigma square, right? So we have that form here. So therefore, this integration, uh, you can get by simplifying this answer, because if you integrate only this part, then you know that is going to be square root 2 pi sigma, right? So using that fact, you can simplify this answer to get 1 over root 4 pi e to the power minus y square over 4, right? So once you get this one, you can easily get this one. Therefore, I'm not going to uh, describe too much of this mathematics. You can do it simply, right? And therefore, if you now substitute the terms into the Bayes formula, we have already got this expression and now we got this expression. So when you simplify those, we get this expression here, right? So we can again identify that this is again the density function of a normal distribution, right? So we are looking at the density function of conditional density function of x given y is equal to simple y, right? So you can see that it's a function of x and y both, but the y is the given value. So here, therefore, we have to consider it as a function of x. Y is a fixed value here, it's a given value. So if you look at this density function in that sense, you can see that this will be the mean of that normal distribution. And this is, you have to have a minus half in the beginning here. So therefore, in order to get minus half, you have to divide by half also. So that half, you can take it as the variance. And then you have to have 1 over root 2 pi sigma, right? And when you simplify that, you will get this part. So therefore, you can see that x given y equal to simple y has a normal distribution with this mean here, and variance equal to 1 over 2, right? So here I'm just briefly explaining the method, right? So you can try to get the answer yourself. Final answer should be then x given y is again a normal distribution, right? So we started with y given x. Y given is x is normal with mean x and standard deviation variance both are equal to 1. Now we have found out that x given y also is normally distributed with mean y over 2, variance half. Right. So that's also an interesting question, interesting example actually. Right. So to explain this a little bit further, we now connect this idea to a well-known statistical technique called regression analysis. In the regression analysis, what we do is we try to find out the relationship between y and x. Y is a random variable. X also can be a random variable. Or x can be some mathematical variable. But in this case, we are considering it as a random variable. So suppose, for example, for a given x, given value of x equal to simple x, for example, y has some distribution, right? For another value of x, y has probably a different distribution, right? For another value of x, again, y may have a different distribution. So the distribution of y may change with the value of x that we consider, right? So suppose, for example, the mean of these different distributions are different in that case. And therefore, let us denote the mean of y given x equal to simple x by mu within bracket x. Just to denote that the mean of y in that case is a function of x, right? So mu x means here the mean of y. Actually, mu means expected value of y given x equal to x, right? So that is what we denote by mu within bracket x here, right? Expected value of y given that x is equal to x is denoted by mu x, right? So this part here, right? And that will be mathematically equal to y times the conditional distribution of y given x is equal to x integrated over y, right? Integrated with respect to y, right? So that's how you get that value. So now I will show you pictorially the situation that we are considering. So suppose for a given x here, right? Suppose this value here is say x1, right? So this is the x-axis, x-axis. This is the y-axis. So this is x1. Suppose this is x2. Suppose this is x3. Right. So in usual simple regression situations in a scenario, what we assume is for a given x, y values, there are several large number of possible y values. Right. More values will be somewhere around a center, and then there will be few values here. And therefore, if you look at the distribution, it will have some distribution like that. So suppose the mean of that distribution is this point. And then when x is equal to x2, again, y can have different values, right? And most of those possible values will be around here, right? There will be several y values, same y value around this value, and then but few values here, and thereby the distribution will be something like this. And for x equal to x3 also, I will have some distribution. So suppose the mean of these possible y values or the distribution, this distribution is here, and mean of this distribution is here, and mean of this distribution is here, right? So what we are really interested in a regression scenario is how this mean is changing. Mean of y is changing with x. So the question is, we want to find out a relationship between mu x and x, right? So we may be able to write down this mu x as some function of x, right? Mu x as some function of x. For example, it may be alpha times beta x, in which case we are assuming that it is a straight line, or it may be in the following form, alpha times beta x plus gamma x square. So it may be some sort of quadratic function, or it may be alpha times e to the power beta x, some kind of function going up like that. So generally, in a situation where we are considering y and one x variable, we may be interested in finding out the relationship between this mu x and x. So that is what we call the regression analysis, simple linear regression analysis, if you are considering a linear function, right? Linear function. Actually, in that case, linear does not really mean a straight line. In that case, actually, this function is also is a linear function, is also a straight line. But in that case, this will also be considered as a linear function because the word linear in that case means linear in terms of the parameters. So here the parameter has power 1, parameter beta has power 1, parameter gamma has power 1. So therefore this expression, even though it's quadratic in terms of x, it's linear in the parameters. So therefore this is also a particular type of linear regression function. This is linear regression function. So in this case, right, if you write down mu x is equal to alpha plus beta x, we call it a simple linear regression function. If you write down mu x is equal to something like this, it's a linear function, but it is also a polynomial in terms of x, quadratic function, right? And if you write down mu x is equal to something like this, you can see now this is not a linear function in terms of parameters, because this e to the power beta x, if you expand that using the tail expansion, it will be 1 plus beta x square divided by 2 factorial and so on. So it's going to be having quadratic and cubic terms of beta. So it's not a linear function. So therefore, in that case, this will not give you a linear regression function. It will be a non-linear regression function. But of course, you can convert it into a linear function in this case if you consider the logarithm in both sides. Right. So anyway, what I want to just mention is that whatever that function gx that we use to approximate the relationship between mu x and x is called the regression function. Right, it's called the regression. So therefore, we are calling this analysis regression of y on x. Right, we are regressing y on x. Right, so in that case, we will require to find out suitable values for alpha, beta, gamma, depending on whatever the model we use. We'll have to actually estimate suitable values, get suitable values for alpha and beta, gamma, and so on. So that will be discussed later on. If we discussed statistical inference uh, after chapter 5 of this book. Right. So the conditional mean and conditional variance. Conditional mean is the one that we are trying to write down as a function of x. Variance. So the conditional variance will be the variance of this function, this density function. Conditional variance of y given x is equal to x2 will be the variance of this function. Conditional variance of y given x equal to x3 will be the variance of this function. Right. So the variance of y given x can be defined as the expected value of y minus mu x square given x is equal to simple x, right? So this simple x is a fixed value. So at that value, mu x will be a fixed value also. So therefore, variance of y given x is equal to the fixed value simple x is by the usual definition is going to be the expected value of y minus the corresponding mean of y when x is equal to x square, right? And equivalently, we can also get the expression using again a well-known formula. We know that usually the variance of y, right? If you just don't consider the given part, variance of y is equal to expected value of y square minus expected value of y whole thing square, right? So the same idea applies when x is given, right? So the variance of y given x is equal to simple x is equal to expected value of y square given x is equal to simple x minus the whole thing square, right? Expected value of y given x is equal to x whole thing square. The conditional mean describes the center of the conditional distribution of y given x. So that's a measure of the center of the distribution. While the conditional variance describes is spread around that center, right? So here, the conditional variance gives you an idea or value or a measure of the size of the dispersion of this particular distribution around this center. For this, it's giving you the spread around this center, not around this center in this case, right? So that is why the conditional distribution, therefore, is different. Therefore, the conditional mean is can be different. The conditional variance can also be different. But in usual regression analysis, there is an assumption that even though the mean conditional mean can be changing with x, the variance, the conditional variance is assumed to be the same. And in addition to that, usually there is an assumption that the distributions are normal also. So therefore, in usual regression analysis, the assumption, right? If you're considering simple linear regression, the assumption is uh, the distribution of y given x is normal with some mean and some variance. The mean will be changing with x, but the variance will not change with x. Variance will be the same. So that is the usual assumption.